This new chapter is actually interesting. I like it more than the other ones in dynamics. The main symbols we're going to deal with in this chapter are Fg, which is the force of gravity. It's in Newton like any other force. It's measured in Newton. G small is the acceleration of gravity as we know, or what we call the surface gravity. If G is calculated at the surface of Earth or of the planet in general. G is the acceleration of gravity or the surface gravity. It's in meters per second squared because it's an acceleration. G capital is what?
I don't remember, honestly.
It's actually a constant. So G capital is different from G small. Okay. This is what?
I'm trying to remember the constant. Sorry.
Yeah, it's the universal constant of gravitation. When I say universal, it means that you can use it for anything to calculate the force of gravity. It's equal to what? 6.6. Do you remember that?
Times 10 to the negative 11. Okay.
Yeah. It's too small. Actually, you don't need to memorize it. It's going to be given to you in the test, and most probably you're not going to use it. We use the formula mainly without numbers, just comparing between different values. Okay, we will derive the unit of G now. And M is for the mass, as we know. And R is for the distance. We usually use R, not X or D, because we deal with spherical things mainly, like planets, like spherical or oval things, okay? Like planets, moons, and so on. So R is for the distance, it's in meters, M is in kilograms. Now, if I want to calculate the force of gravity on a 60 kilograms girl on the surface of Earth, how do we calculate this?
Mass one will be, force of gravity, or like in the G, M1, M2?
No, the other formula that we used to use before, the simple one.
It would just be mass
times gravity, right? Which is like 60 times
9.81.
Yeah, or let's say that it's approximately 10. Yeah, it's around 600 newtons. Now, we know that G is 9.81 or almost 10 meters per second squared. But where did they get this value from? How did they calculate this value?
They use the radius of the Earth times the mass of an object.
And the mass of the Earth. Okay, so G on the surface of Earth is equal to capital G M over R squared. So this is the formula they use to calculate G. M is the mass of Earth and R is the radius of Earth, if you want to calculate G at the surface of Earth. That's why G is different at a very high like point, let's say 10,000 kilometers from the surface of Earth. It's going to be different, right? It's going to be slightly less. Okay. So this is the formula we use to calculate G. Now, what's the formula we use to calculate Fg then? If we replace G by its formula, Fg will be?
We add a second mass, right?
G, M, and M. So we have two masses now. We need to write M1 and M2. We don't add them. It's like K, Q1, Q2 over R squared, the one for electricity. So this is also for R squared. Actually, for planets, we prefer to use R as capital to say that it's a big radius. Okay, so this is the formula for the force of gravity, Fg. Now, can you derive the unit of G now?
Yes, you would multiply. You would have it as, well, in terms of the equation, right? So it would be G is equal to FG times r squared divided by m1
Exactly.
m2.
So it's Newton times.
Oh,
I want the unit now. You can derive it from its formula as you did.
uh-huh.
Fg is in Newton times r squared. R is
So
meant to be what?
meters.
So yeah, it's in meters squared over m1 times m2
Kilograms squared.
kilograms squared. Yeah, so this is the unit of G. Okay, Newton meter squared per kilogram squared. Now, do you know that whenever you have two masses, m1 and m2, with a separation distance between them, there will be a force of gravity between them. Do you know this? They will attract each other. But we don't actually notice this force between us because it's too small when you compare it with the force of gravity with Earth. So let's calculate the force of gravity between two girls, a 50 kilogram girls and a 60 kilogram girls, and compare that force with their weights, the force of gravity on them. Okay? If you want to calculate the force of gravity between these two masses, it's going to be what?
300 times 6.67 times 10 to the negative 11
Times
divided by
11 times m1 50 times m2 60, or 300 as you said, 3000, sorry, over r squared if the distance between them is like 1 meter. Let it be simple.
what divided by 1 meter.
Squared, which is 1. This is going to be what? Do you have your calculator?
I can use my phone if that's all right. Let me pull up a calculator. Scientific calculator. Yeah, I have the same one as you right now.
Okay.
So 6.67.
I actually got it. I just opened the
Oh, right.
219. Okay. So it's like 20,019 times 10 to the negative 11. If you want to represent it in a better way, you write it as 0.2.0019 times 10 to the negative 7, right? Look, it's too small, right? If you compare it with the weight of this girl, her weight is about 500, right? Newtons. And this one, her weight is about 600 newtons. This force is much, much less. So you cannot compare this number with that. That's why we don't feel actually that we're attracting each other like magnets, while we actually do. There is a nice video, I like that you watch it. I will just show you a short part of it. Do you know this channel? Vsauce?
Yeah, I've heard of him.
Yeah, it's a very good channel, by the way. I like Michael. His way of
I've seen a
introducing
video on inertia where he takes like a metal pole and spins it around.
Yeah. It's one of the best channels actually for science. So
it can sometimes be thought of as where you are. This said, mass of is just you and the Earth being attracted to one another. Now, every portion of an object with mass attracts other portions towards it. The average of all this pulling is an attraction between centers of mass. Giant things like Earth exert an obvious pull, but everything does, even a baseball. These two baseballs are attracted together by their own gravities. Except their masses are so small, the force is minuscule, and it can't overcome friction or push air out of the way. They're never going to come together. But if you put two baseballs 1 meter apart in the middle of empty space where no other forces could act on them, they would literally fall together and collide. It would take 3 days to happen, but it would. Isaac Newton found that the strength of the force bringing two things together is equal to the product of their masses divided by the distance between their centers of mass squared times big G, the gravitational constant.